Today, our speaker is Qunsheng Huang. We also call him Keith, and he's going to give us a compilation talk. He will tell us about redefining lexicographical ordering, optimizing Pauli string decompositions for quantum compiling. And the floor is yours.
Okay, hi, good afternoon, or good morning, everybody, or good afternoon, everybody, depending on your time zone. Yes, thanks for the introduction, and thank you so much for the invitation to present some of our work. So this work was done in collaboration with one of my master students, David Vindel, Ariana Maya van der Griend, as well as from Helsinki, as well as Richie Young from the University of Oxford, and now with Continuum. So the general idea for this overall work is basically a compilation of time evolution operators, which consist of weighted Pauli strings. So basically, if you have some series of Pauli strings, Sn, of some arbitrary length, and then you have weighted some of them with some weight parameter theta n to give yourself a Hamiltonian. We want to basically compile the time evolution operator to a quantum circuit and somehow run it. And for that, we use the very common method of first order trotterization, which ends up looking something like this. Once you just squeeze or you just mash all the various constants together. So you end up with these series of terms that basically have an effect on a number of wires or qubits, such that each of them is fully represented by some angle, so combination of the weighting term as well as the time step, for example, as well as a Pauli string, and each of them represents the exponentiation as is normal. So the relevant thing here is that given this form, you can arbitrarily reorder the terms without changing the order of Trotter error. So utilizing this in compilation is not something new. I have some links at the bottom, which people have not only investigated what is a good way of performing this reordering for circuit compilation, but also what the effects of this ordering is. So generally speaking, people implement something like a lexicographical ordering, which is just a very complicated way of saying an alphabetical ordering, where you define the strict ordering of different Pauli letters, I included, of course. And the general realization is that, yes, if we just strictly order the terms, this gives some benefit. This allows us to work with large chunks of somewhat similar terms on the same wire at the same time, which means that one single operation can affect multiple objects. And this ends up leading to circuits that are just smaller. However, we approach it from a different standpoint. So the thought is, okay, why do we need a strict ordering? Why don't we just choose an ordering locally that works the best for what we have on hand? And that's where we're going from. And then I guess the idea is then also to include some architecture-aware compilation, so that when we do so, we map it to some underlying architecture connectivity map. So in this case, we're generally working with hardware that is superconducting qubits. So noticeably the connectivity constraints or layout constraints of neutral atoms or ion traps do not work with this, but that may be future work. And the goal, of course, is to minimize the circuit depth, but also pay attention to CNOT count as well as CNOT depth. In this compilation strategy, our entangling gate is the CNOT, which is why we have chosen these parameters. So just to give some reason to continue listening to the talk, we have provided some numbers on this page. They give an idea of how much improvement we see when comparing our compilation method to existing methods out there. So we're comparing with Paulihedral that also employs or utilizes the idea that you can just reorder things if you have this first order trotterization, as well as TKET and TKET, well, set and pair, which are slightly different variants of also very similar algorithms. And we see that when we compare the overall circuit, in this case, this is circuit depth. And the thing that we are compiling is actually these molecular Hamiltonians. And this basically comes from the benchmark set that's used by TKET and is also used in the various papers introducing the other methods in order to perform a comparison. And we see that when comparing the second best case, our proposed methods do show an improvement of several thousand gates. And this kind of that shows the efficacy of performing this ZX calculus-based synthesis strategy with dynamic ordering. So before going any further, I need a few preliminaries. So I think considering the name of this conference or this this discussion forum. Everybody should be very familiar with ZX calculus, so these symbols should not be strange to you. And one thing to note is that these are the basic elements we use to modify the Pauli strings, or the Pauli string representation in ZX calculus in order to perform the circuit synthesis. One thing you'll note is everything here is a Clifford gate, which is actually very important. And we'll talk about that in a second. But moving on one step further, I just showed what we use to manipulate the objects, and now I introduce the objects themselves. So if you recall the blocks on the circuits in the previous screens, we can actually, there's a very intuitive way to write things down in a ZX calculus dialect. I first became aware of this in this paper by Carlton, this general compilation strategy for the UCC A, basically the unitary coupled cluster ansatz. And basically, given this Pauli string, I, X, Y, Z, with some constant rotation angle, etc., theta tilde, we can write it down as a central white block with theta tilde, and then blank Y represent the identity. I'll refer to this often as the identity leg, because you do have to keep track of this in some cases. And then X, Y, and Z representing the corresponding Pauli letter on the respective qubit or wire. In this case, I think the strangest thing should be this Y leg, which is half red, half green. Otherwise, everything can be treated pretty similar. And in future diagrams, we will omit the letters. So this page just to show the mapping between the block and this Pauli gadget representation. And this is how we represent the individual elements that come from the weighted sum in the Hamiltonian. And now that we have introduced one, what we use to manipulate these blocks, and two, the objects themselves, we talk about some equivalence relations. So in ZX calculus, this is the main draw. When you have something on the left, and then you can show through some rewrite rules that's equivalent to something on the right, and use this to perform some manipulations of the object. I won't go any further because I'm sure you guys are very familiar with this. But stemming from here, we introduce these subroutines that basically don't change anything. And the main way we do that is by introducing the identity. In this case, we'll introduce the gate and the adjoint, where the adjoint, when propagated through the series of gadgets that we're manipulating, will enact the change that we want. In this case, if you have this particular setup, i.e. if everything on the top wire is a Z leg, everything on the bottom wire is a Z or a Y leg, running a CNOT through simply disconnects the top wire. And this is what we call disconnect Z or Y. And this is one of the two main subroutines that we use. The other subroutine very simply maps any leg on a single wire to the Z leg, because we use this very often. These are the other disconnect rules, which also and this page I'm here to show you because the disconnect itself has some limitations. So disconnect can only really work with two legs on the second wire, and always assume that the leg on the first wire is a Z leg. And we can, of course, get there by using a single Clifford gate in any of the examples. You can map an X or a Y leg to a Z leg very easily. But the key thing to note here is that after you map everything to what you want, there's always going to be a series of gadgets afterwards, which do not fall into this category. And so when you perform this disconnect operation, oftentimes what happens is that the unsynthesized, so the gadgets that have not yet been synthesized or are partly synthesized will be modified. And you have to keep track of this as you're performing the compilation. One more thing to note in each of these rules is that there's these dotted lines that separate the overall result into three different portions. At the very left is the quantum circuit. In the middle, I'm going to tell you these are the Pauli gadgets, which are partially synthesized or unsynthesized. And finally, a tableau on the very far right. And if you're familiar with the name, this is exactly a Clifford tableau. Which is not extremely relevant to this talk. However, it is a nice way to store a large amount of Clifford gates, mainly because we also have a nice way of synthesizing a Clifford tableau in an architecture-aware manner, which I have shamelessly linked our previous work at the bottom of the screen if you're interested. So we'll not go into this, but the general idea is that as we're synthesizing, we produce a large number of these Clifford operations, which we propagate through the entire circuit. We store this at the very end and resynthesize this in an architecture-aware manner at the very end of the overall compilation. So this is what a Clifford tableau is and how it works is not super important. The main thing to know is that we're able to split the overall synthesis, or you end up with 3 different chunks every time we run through the various synthesis steps. The very left chunk is then just appended into what forms the quantum circuit that we are creating at the very end. Okay. Now I've introduced the various components. So we have this Pauli representation, we manipulate them with gates, we introduce them, creating a circuit on the left and storing all the leftover or propagated Clifford operations on the right. So now what I'm going to run through is the general idea, given this series of Pauli gadgets, what we're doing. So this is some very simplified representation, and I've drawn it this way so that this is basically a series of Pauli gadgets on a line architecture. So only the neighboring qubits are connected in the underlying hardware. And the first thing we're doing is that we're going to choose one qubit to attempt to disconnect. Then, using some cost metric, we'll talk about later. Once that's done, we will gather the gadgets that can be disconnected. So recall that there's some limitations. Oftentimes you cannot disconnect if there are multiple types of legs on a particular wire. So you simply ignore those and only take those that you can work with, basically. Then find a neighboring qubit to disconnect from. There's another cost function, which I'll talk about later. Form the disconnect, and then return to step 1. You can see that some of the one gadget is not highlighted and the rest are highlighted. So basically, we basically end up with a smaller and smaller scope each time we perform a synthesis step, ignoring everything that's out of scope, and then just recursively go back once we have finished synthesizing everything on hand. And this is the very, very general idea of how the overall algorithm works. And now I'll go into a more step-by-step example and talk about the various considerations at each step. So now we're looking at a time evolution operator with 4 components and some underlying some underlying line architecture represented by G. I noticed now that I should not name both of these G because of confusion, but I was copying the notation in the paper that we wrote. So anyways, the bold G represents the scope. So what is currently in scope, and you'll see this shrink during the various steps of the algorithm. And this capital G represents the underlying architecture. So the first step, as I mentioned, the simplified example, is to choose a qubit to start with, and we refer to this as a pivot qubit. Using some heuristic H pivot, the exact heuristic, more specifically, looks for a wire with a large number of identity legs, as well as a wire that has a single dominant type of leg. And it's represented by this equation here. So it looks complicated, but it's actually very simple. The capital P's are simply a counting function given the Pauli letters that lie on a single wire. So here, Pi simply counts a given wire Q, and the Pauli gadgets that are in scope count the number of identity legs on this wire Q. And we multiply this by some constant factor. So we actually heavily weight looking for wires with a large number of identity legs. Then P max, P min simply counts, find the Pauli letter that is most prevalent on a leg, and then count the number of these. And so you want to find a very dominant number of Pauli letters, or a single Pauli letter that dominates. So you take P max minus P min, and these do not count the identity letter. They only count X, Y, Z. So for example, just to find what the number is for a single example, we take a wire 0 or qubit 0, and we say and we see that S0 G basically gives us the Pauli string or the Pauli letters on that wire moving left to right. The ordering is not super important because you're simply counting, but just to remain consistent, it's I, Y, I, Y. And so the number of identity letters is 2. The maximum the number of dominating Pauli letters is 2, which is Y, and the min is 0, which can be Z or X. And so if K is equal to 10, then the output of this cost function, given wire 0, is going to be 22. And we use this to basically find the next qubit that we're working on. So recalling that we want to remain architecture aware, all we do then here is to just ensure that all the potential qubits that we're looking at are non-cutting. and which takes in all available qubits in scope, as well as the connectivity graph. And what this returns is, what this means, if it's non-cutting, is that if you remove it from the graph, it does not result in two disjoint graphs. With that in mind, we see that only two qubits are viable in this step, the ones at the end, because removing anything else will result in two disjoint graphs. And when we compare the two, we can see that the first qubit has a much higher number if you throw it into the cost function, and we choose it as our pivot. Once this is done, we move on to the second step, where we gather things together. Here we gather the identity leg together and then proceed. If you notice that there's a step 2 here, it says replace gadgets with only one non-identity leg, return if no gadgets remain. This is our recurse step. So basically, as the scope reduces, at some point you run out of gadgets, and this then results in a recurse step up, and you basically go to the previous level where there are still things in scope, or you terminate otherwise. But then after this check, there is no such gadgets. So we simply group legs on qubit 0, and we see that there's a large number of identities that we can group together. This is an artificial example, and we set it up this way for this specific case. So this is the point where you can see that this is our dynamic lexicographical ordering. We group things by legs, and then if there are no identities, we just take what is the most dominant letter. So here we will change what the strict ordering is depending on what's locally there, which is slightly different from what is done in other algorithms, which simply implement a strict ordering throughout the algorithm that does not change. And these are examples of the papers that do something similar, that organize them in such a way or set things up in commuting sets or in good pairs, basically. Yeah. So what we see is that once we group things together, all the identity legs together on the same wires, we can easily ignore them because there's nothing that remains to synthesize on those wires if we ignore everything that is not an identity leg. So what happens here is recurse down. We see that in the next wire, everything is still identity, and then we recurse further, reducing the size of the problem. So this kind of explains why we have this choice of cost function, because we just want to ignore things we don't need to do as fast as possible. This comes with other problems, but I'll talk about that in a sec. But at this point, now we have recursed down, ignoring wires 0 and 1. We immediately look for another pivot qubit, returning to step 1. And we see that there is a dominant letter on qubit 3, which is the Z leg. And so we choose that as the pivot qubit. Then we need to choose a neighbor qubit using a different cost function. So the underlying heuristic is still the same. The only thing is the support for the function. And because we want to remain architecture aware, if we ensure that every time we synthesize two neighboring qubits, we ensure that they're always connected by an edge in the underlying connectivity graph, then whatever is synthesized will always be architecture conforming. And this is exactly what we do. The cost function remains the same, but we only have one candidate, so the choice is trivial. We move on and perform the disconnect subroutine, which was introduced at the very beginning. Surprise, surprise, we have constructed so this only requires a single CNOT to propagate through. This is also the step where if on the neighboring qubit, there's an identity leg, there's actually a choice here. We have, if there are gadgets that have an identity leg on the neighbor, we actually have to flip the identity over to the pivot qubit. So this is important because if we do not do this, it will result that we will re-entangle specifically the partially synthesized Pauli gadgets again in cases that we have already ignored. So we have to make sure that whenever you perform the disconnect, everything in scope must not contain identity. Otherwise, you reintroduce entanglement at some point in the future, and you end up in this non-terminating loop. However, in this case, this is not true. We have artificially set up this example, so there's no identity of in scope, which means that we can perform the disconnect and propagate the CNOT through, and we end up with a very simple case. One additional thing to note is you look at the gadgets that are out of scope. Because of propagating CNOT, we introduce entanglement there. So we have to keep track of things out of scope, even though we are only modifying a smaller number of gadgets and a smaller number of wires. Once we reach this point, we've done the disconnect. We note that we have actually hit the return step because everything remaining is a single gadget with only one leg. There's non-identity, which means we can replace it with a rotation gate and then return. And this is what it looks like. So in this point, the algorithm only synthesizes Z rotation gates, which means that we just perform some step to map it to a Z leg before synthesizing the rotation gate. However, this is easily modified. And once we synthesize these rotation gates, everything in scope is complete. The scope is empty. And so we recurse one step, or at least two steps up to the original recursive level of recursion, and return to the point where the qubit 0 is still our pivot qubit. And then we'll proceed by grouping, disconnecting continually until the entire circuit is synthesized. So I skipped over the next few steps because it's more of the same. But this is effectively what you end up with once you run through all these steps in our compilation algorithm. So a few things to see here. So everything on the left has been synthesized as a quantum circuit, and everything on the right inside this box is stored in a Clifford tableau. And we can synthesize this using an architecture-aware algorithm, and oftentimes this leads to some reduction in depth. This is especially the case if the circuit is extremely long, because one of the results from our previous work is that you can throw as many gates as you want into a Clifford tableau of a certain size, and the number of gates which return from an architecture-aware synthesis has some asymptotic bound. And we theorize that there is some information limit in this Clifford tableau, and at some point, you just end up with a similar depth of circuit, no matter how many gates you throw inside. The second thing to note is that we only synthesize half of a ladder. So if you're aware of the naive methods for synthesizing Pauli gadgets, you often end up with basically some rotation gates or some Clifford gates on the outside, as well as a ladder of CNOTs with a rotation in the middle. And in this case, what we've only done is synthesize half of the ladder going in whichever direction. So one thing we theorize is that why our method works very well is because this allows for more transverse operations to occur. Because if you have lots of halves of CNOT ladders, there might be more transverse operations there. And we see some interesting results when we compare with other state-of-the-art algorithms in a second. Yeah, I've run through basically what our algorithm
may I ask
is.
a question?
Sure, yes,
So
of
when
course.
you said transversal, do you mean unitaries that acts on single qubits?
Sorry, no, when I say transverse, I just mean that gates that can run in parallel on a device.
So they can be squeezed into one time size.
Exactly, yeah.
Okay, thanks.
So that's what I meant. Yeah, so if you have half, and then if you have, for example, half of two identical ladders, then half of them can be transverse, or at least you can stack them one on top of the other. So we theorize that there's more chances of parallelism or more chances of squeezing multiple gates into single slices. And that's why we see some improvement there. Yeah. So now that I've run through the overall algorithm, I'm just going to run through some results. So we ran 3 different experiments, the first of which is random Pauli polynomials. We looked at different IBM architectures, going from 5 qubits to 65 qubits, and then for a different number of gadgets. We randomly generated Pauli gadgets, so random type of letter on each leg, and up to a certain number. So basically, I think every 20 or 40 gadgets was one data point. You generate 20 random Pauli polynomials, run through the compilation algorithms that are seen on the screen. So Paulihedral, TKET, you see as the set and pair, as well as a naive decomposition, as well as our proposed the decomposition, and compare the results. And our results are in pink. We note that this synthesis is on architecture, which means that for all the algorithms that are not innately architecture aware, an additional routing step is required. And we use the innate TKET routing strategy. So you can see in the case of comparing our algorithm to non-architecture aware algorithms, there is this inherent cost of routing, which is what I assume is going to be the reason for the large gap between our pink proposed method and the other methods as the depths increase. So we also increase the step size for larger circuits, but we didn't see any strange patterns. We saw very straightforward lines, so we didn't have any stricter discretization. We see that as we increase the size of the architecture, the percentage difference between our method and other methods remain roughly the same. But however, this also is several thousand gates in each of these cases. And we kind of expected this behavior simply because we do the routing step in compilation, and for the other synthesis algorithms, additional routing is required. Yeah, we do notice actually at the very, very beginning, if you see that it's hard to see, but basically we do perform worse if the circuit is shallow enough. And one of the reasons for this is we noticed that for a very small number of gadgets, there's a tendency, if we start with a non-identity leg, that we tend to route through or swap through a large number of identities because of our cost function that always looks for neighboring qubits with large numbers of identities. So that's something to work on. But after a certain depth, this behavior does go away. And of course, we also ran all these experiments on all-to-all connectivity in which no routing is required, just to see how it compares with other algorithms straight up. And we see, so first of all, we also still see the same behavior where our proposed algorithm does not perform well for shallower depths. If you see, the first thing is CNOT count. For CNOT count, we actually don't really see any major benefits of using an algorithm and all-to-all connectivity. But we do see an improvement when we're looking at circuit depth as well as CNOT depth, or 2-qubit depth in this case. And we see that there's a very significant improvement on these counts. And the reasons for this, I've mentioned already. One, we throw a lot of things in a Clifford tableau, and we see that there is an asymptotic bound on that given number of gadgets. So it may be the case that that's helping us. Secondly, is the chance for more transverse operations in the circuit because we don't synthesize the full size of the full ladder. Yep. The second experiment that we run was on the benchmark set used by TKET when they were showcasing their various compilation strategies. So these are various molecular Hamiltonians using particular methods to map it to a qubit or a bosonic system and then synthesized. So what we did here was to take the next largest IBM hardware and then perform the compilation on that hardware using the hardware connectivity. So for example, for the smallest molecule, which is 2 qubits, we ran on Quito, which has 5 qubits. So this is synthesis onto a restricted architecture. And we see that in these smaller cases, actually in the first 2 cases that are in this table, we do actually perform worse on almost all counts. And we believe it is mainly because of a qubit choosing heuristic. However, for all the other larger molecules, we do outperform on every metric. So in this page, this is CNOT count directly, but then we see this for CNOT count, CNOT depth, as well as circuit depth in general, that we outperform very significantly the next best algorithm. Yes, I was made aware last week in IEEE that there have been new algorithms that have been introduced that also do this particular compilation, but we have not yet had time to compare them directly, but they are out there. I have not yet been made aware of any new algorithms or new compilation algorithms that do our particular routing methodology, which uses CNOTs instead of swaps directly. But yeah, that's also something interesting to look at in the near future. Yeah, with that, that's the end of my reasonably short presentation. We've introduced a ZX calculus compilation strategy that does routing without swaps and shows improvements with some of the state-of-the-art algorithms that are currently out there on the different metrics that we've raised. And we want to target, and for future work, we want to target improving the pivot qubit choice. Perhaps there's a nicer heuristic to use, some AI strategies perhaps, as well as qubit placement. Because one thing that you should notice that we actually use a naive placement to start our algorithm, where some of the algorithms that we compare against actually use a smarter placement algorithm. And this could be done perhaps by using reverse traversal, perhaps also other AI methodologies. And we have some ideas from last week's IEEE as well that we want to try and implement. overall, the research was partially funded by the various groups below. Um, Thank you very much for your time and your attention. Um, yeah, if you have any questions, I would be very happy to answer them. Oh, I don't have the paper. I need to check the papers directly, but there were a few. There was one that basically did a search of a full-on dictionary, full-on search of mapping. So you actually do a dictionary search at the very end when you have a starting Clifford circuit or something like that. What else? I think Qiskit also introduced a new weighted Hamiltonian. So basically, this Hamiltonian made of weighted Pauli strings. Ansatz, Qiskit recently introduced a way to perform this compilation. I actually don't know how that works, but it was introduced, so we might just want to run and see how it compares. Um, Let me see. We got some ideas on how to do qubit placement a little bit. There is a force routing paper from IEEE. I don't know when it will be released that uses that kind of makes artificial forces depending on which qubits are entangled by gates. And they use this to do routing, but I think you could also extend this to do mapping, which would be interesting to look at. But yeah, those are what I can think of off the top of my head.
Thank you, Keith. So everyone, if you want to give Keith a plug, you could just use the emoji or, just whatever that suits you. And if anyone have questions, feel free to turn on your mic or just post it in the chat. So I have a question. Well,
Mhm.
since maybe other
Yes.
people needs to think about it. So I wonder, you're talking about the routing on the linear topology, and then notice that in the
Mhm.
benchmark, you're looking at qubits more than just four. You have qubits number
Mhm.
20 or more. I wonder if you're using IBM as your benchmark architecture, then their topology is heavy hex. Is
Mhm.
the assumption of linear topology like still like reasonable because that their heavy hex is not linear, right?
Oh, apologies. Yeah. So, the linear was only to make it easier to see on the presentation.
Okay.
When you look at the heuristics, the main thing is that here, when you look at neighbor candidates, you always ensure that the candidates are connected to the pivot qubit by a hardware edge. So this can be for any architecture. So what we mean is that because we change the support, we ensure that architecture connectivity is conformed to whenever we choose a neighboring qubit. So whenever we want to synthesize an entangling gate.
Right. Thank you. Um, Anyone has a question for Keith? So I'm curious about the Clifford tableau that you mentioned in the middle of your talk, where you said the Clifford tableau is basically like this classical memory that you always know how to synthesize. But before you get this, you have this kind of like a Clifford tracking, so that you have the circuit that is composed of the Pauli gadget that you synthesize. I wonder, have you looked at if you don't do the full Clifford tracking, if you only do
Mm.
half of the Clifford tracking, so that you presumably preserve some Clifford in the middle of your circuit, but maybe this will give you lower weight Pauli gadget to synthesize. Have you
Mm.
compared different degree of Clifford tracking and how much reduction that would give you in terms of the CNOT count and circuit depth?
Um, so the I guess it's because we constantly swap things around. So we constantly reorder. So every time we do a recursive step down, it's possible that we sort things again and again. So we reorder them because we group the light legs together. And if you keep any of the Clifford gates in the middle, there's a chance that you need to do more tracking of whatever is being swapped, depending on the position of the gates, I think. So in order, I think it is simplicity that we just push everything to the back. Um, if there is a way to ensure that nothing crosses the Clifford gates there in the middle of the circuit, then that could be something we could consider, I think. But I think that's an interesting idea. Just not so sure how to implement it.
Thank you. The CNOT count, CNOT depth, and also the circuit depth. But from the recent literature, it seems that there is this like trade-off between optimizing circuit depth versus optimizing the gate count. In running your benchmark, have you noticed like is there a way to tweak your parameters or like in the middle of the pivot selection that you can prioritize optimizing certain metric so that you could get the gate count optimized routed circuit as opposed to the depth optimized routed circuit?
That's a good question. I don't think there is something that we can easily switch at the moment. I'm aware of these trade-offs. One thing that we were thinking of is also, if you recall, when we synthesize a molecular Hamiltonian onto some hardware, it's very possible we have leftover qubits. We were also thinking of maybe trying to utilize all the qubits in some way. I'm not so sure if this answers your question.
Wait, but do you mean like this qubits could be used as like ancilla? Like what do you mean by reuse them?
Yeah, exactly. So something like ancilla to minimize depth further or something along the lines. No, I mean the simple answer is no. I don't think there's an easy thing we can toggle because to be fair, our qubit pivot heuristic is very simple. And that's something we want to also look at in the future. There may be a heuristic that improves that allows you to perform this trade-off, but I'm not so sure how that would look like. But yeah, that's something to think about in the future, definitely. Yeah.
Thank you.
I have a question.
Yes.
So with this this heuristic, I don't know if you mentioned, but have you considered using a machine learning approach to trying to choose the heuristic?
That is exactly one of the things we want to look at in the near future. I think that like the reinforcement learning methods for ZX compilation is something that people have looked at with some exits, some levels, some degrees of success. So I think that's definitely very workable.
Yeah. No, it looks like the perfect opportunity because you've just got a simple freedom of choice on the qubit.
Yes, that's true. Yeah. I'm not very familiar with machining myself, and I'm asking around for help. But yeah,
maybe we should talk about it.
If you're interested, why not? I'll be very happy to collaborate.
Yeah. Another thing about the heuristic is I'm not too familiar with quantum circuit architectures. I'm more on the algorithm side. But does the heuristic change much depending on the way you want to synthesize the circuit? For example, which architecture you're synthesizing it for?
Okay, for our experiments, we just went with k equals to 10. Actually, what you see on the screen is produce all the results. I think that the exact heuristic may need to be somewhat tailored, or like you need to play around with the constants when you move between architectures. I guess that's one of the downsides of working with IBM architectures all the way through because the layout is somewhat similar. We see different behaviors if we move to a different architecture. So mostly yes, but I don't know.
Interesting, thank you.